Hello, everyone. I'm Shu-Qing from School of Civil EAS, University of Wollongong, Australia. Today, I'd like to introduce you the near boundary fluid mechanics. I will tell you why this is an important book, just published by Elsevier in series Multiphysics Advances and Application. Before I start, I'd like to cite Heisenberg's words. When I meet God, I'm going to ask him two questions: why relativities and why turbulence? I really believe he will have an answer for the first. Heisenberg was a Nobel Prize winner, also quantum mechanics founder. In my opinion, fluid mechanics is not so difficult. So I'd like to show you why. First of all, mechanics comes from Newton. He published his formula in this year. In this book, this book definitely everybody knows changed our history, changed the world. Unfortunately, this book has not been applied to fluid mechanics. In this book, he proposed how to determine the shear stress, that is viscosity, velocity gradient. Based on this one, we know the shear stress here and the pressure force here. We only have two forces for fluids. And this is for external flow. For internal flow, this book says same. Only need to concentrate in the near boundary region, because far from the boundary, this velocity gradient equal to 0. No any energy loss. And the fluid can be treated as ideal or invasive fluid. This is why Sumantara, Indonesia tsunami earthquake can kill the people in Africa over 10,000 kilometers away. No energy loss. So this book, for this case, saying you only need to concentrate on the near boundary region and far away from the boundary, and then we assume no energy loss. This one is totally different from other books and partially agreed with Planck's boundary layer flow. That is, this book says for any control volume, CV, we have the body force, gravity, and shear stress and pressure. For the pressure, we do the integration over the surface, and we have this formula. And here the P is pressure, and we can always express P with density, gravity, and some height. For example, for atmospheric pressure at the sea level, we say H is 10 meters, this pressure. Pressure can be always expressed as the fluid height, H. H and A put together, dA, that is volume. So we will say pressure drag is a volumetrical force. For this one, you use this formula, and then you will see this pressure difference here and here is the same in still water, and here will be difference. The integration will generate the Archimedes' first law, displace fluid volume here in the vertical direction. If this one is moving like a car, train, airplane, or submarine, and then the vertical one could be the same, but this one will be no longer equal to each other. This integration in the horizontal direction will be like this one. Pressure here will be higher, pressure here will be lower, like this. And then the higher pressure in the upstream and minus the downstream pressure for this case. And then we can always express this one as upstream pressure as the function of Fu. And LO equal to this one in meter. Same in the downstream here, we can express in this one, and then FD is the distribution function. What kind of function we don't know, but if we have the measurement pressure here very large, here will be small, and here will be the same and smaller, and then we will have this curve. This is the distribution P FR minus FD, like this. Multiplied by this one is this warning. So we get the second Archimedes law. This one becomes the weak fluid warning. So our one will say that weak warning is larger and the drag force will be larger pressure. Both of them follow the same formula, and Archimedes' principle becomes a special case for this formula. This one is more general, universal for hydrostatic or hydrodynamic pressure drag. This is my first contribution to this pressure on the surface. In the surface, we have the pressure. We also have another one, is we call it as shear stress or friction force. And Newton, as I mentioned, in this year, developed this one. About 200 years later, they give another term. They shear stress, now we call it. And about 150 later, this year, we published this book, and then we have one more term here to include for shear stress in turbulence. And I like to say, I will explain to you why this one is important later. And now look at boundary shear stress here. That means this 10 and this 10 will be equal to 0. Only Newton's formula is wanted here. How to determine its distribution, we don't know. To solve this problem, I proposed turbulent energy is transferred toward the nearest boundary for dissipation by friction or shear stress. What this means, if we imagine this is our classroom and this is our student, we give the order to student, everybody move to the nearest boundary here, here, here. And you will observe the student will move along the normal line of the boundary here to stand here. Same, all the students in this region will move to the side wall, but the student will remain in his position unchanged. Why? Because this is bisector. The normal distance from here and here is the same. My order is nearest. He has no nearest, so he has to stay in the original place. Same for the student, same for the student. This is what we say division line. If we look through the two normal lines, and then we can imagine all the students will come to this region, theta P. And then if we ask you to determine the boundary shear stress, you will say all the energy, potential energy loss from high elevation, the mountain, to the channel, to the ocean, and then that you lost the potential energy. The potential energy will be converted to the friction force, I, at the boundary here. That means a potential energy loss is this one, divided by theta P is this one. So the boundary shear stress is proportional to the normal distance from here to the surface or from here to division line. So we have this curve. And then similarly in the vertical, in this better region, and then we say the normal distance is the vertical line, and then L will be proportional to this distance. We will have distribution like this. And here is the measurement data for rectangular channel, trapezoid channel. Trapezoid channel change the angle, and then we can see all of them that the agreement look very good. So we solve the first one. Now we answer the question, why we should have another term, this one, vertical one. Okay, before I talk about this one, I also surprised me to notice that for the snap, for structural engineers, if you increase the loading and then the snap supported by the beam in the shaded one, and have the yield line like this one, will be the same as our division line. For geotechnical engineers, you have powers to the ground. If you want to know this soil in this region will be affected by which power pile, and then you can also draw the link this one, normal distance, normal line, and you can say this region will be affected by this power. And then this region, soil will never affected by this power, should be affected by this power. This is assumption. I don't have the experimental data. Now we answer why here vertical velocity or normal velocity will be important. The first one who noticed this one comes from Einstein. His eyes is different from us. Everybody had the drinking tea experience. When you stir your water, you will observe tea leaves concentrated here. And then he asked the question, why? Without any experiment, he published a paper, and then drew these two circles, say the tea leaves are transported by this secondary current, and then from here to the center, from here to the center. This is why tea leaves concentrated at the center. And more than that, he extends this one to explain why the rivers keep moving like a snake, because sediment will travel from this bank to another bank. So this one keep moving, and then he very successful. And then here he didn't have the mathematical expression. This is the vertical velocity. He missed this parameter in his theory. He didn't develop any equation to express his idea. Now I developed these equations to include this parameter, that is y Young's parameter. Omega is tea leaves of sediment settling velocity. If y equal to 1, that means your 1 is very large, and then this will be equal to 0. Your sediment's apparent density will be equal to the water's density. If y is larger than 1, and then you can drive your tea leaves to the surface. And then this one is positive, and another one is negative. This side negative. This one make the tea leaves heavy, very hard to remove. This one make the tea leaves looks like milk, becomes light, because its density is different from the natural density of tea leaves or sediment. And almost at the same time, in this year, Nicholas measured the velocity in ducts. And he showed this his measurement to his supervisor plant. And without experiment, he is very smart, as smart as Einstein. He immediately tell in the duct channel, you should have the secondary currents. Also similar to this one, we have the vertical velocity like this. And then, but we don't know why. Till now, nobody can tell the reason, driving force. Why fluids not go a straight way, does not want to go to straight way, but in a rotation way. I look at the same problem and I follow Planck's formula. And then this is the formula we say governing equations. You can see we have two terms, partial differential in y direction and z direction, and put together equal to constant gravity and slope. This one constant. This is partial differential equation. You can solve. And he is very smart. He say in the near boundary region, you can only the vertical one or normal direction one is useful. And another 10 can be dropped. And he dropped this one to the lattice spin. And only have this 10 left. And solve this equation and got some important conclusion. Over 100 years, and everybody use the same way in fluid mechanics community. And I pick up this 10 from Planck's lattice spin. And I found this is another partial differential equation. By solving this partial differential equation, I got this horizontal velocity should be proportional to velocity gradient in z direction. So here, if you see this direction is not proportional to your boundary, and then you can observe the secondary currents. Because of this one, we have the V. Why? Because our V come to up and must turn to satisfy here the shear stress equal to 0. To satisfy here, shear stress equal to 0. Here, shear stress equal to 0. Here, shear stress equal to 0. Your one must turn, and then no particles can penetrate the boundary. This like a grass, invisible grass. And then to make sure here the shear stress equal to 0. So this is why we should have one more turn here. And now we define the pressure, we define the shear stress. Now we define the acceleration. This is the latest experiment in 1983 in University Manchester. In this experiment, he found the laminar flow and transition turbulent flow or turbulent flow. And he proposed the time average method. We say now everybody knows latest method, time average method. I stand up and now I say this one is too simplified our problem. Why? Because to make our assumption of acceleration is equal to 0. Our hydrodynamic problem has been simplified as a uniform flow condition. In fact, this is the dynamic without the information of acceleration. Why? Look at this one. When your fluid start to move from here to here and on the x direction, and we can have this equation. We say this is mass conservation. And then V, U is horizontal, V is vertical. And then you do the integration, you will see if U is increasing in x direction and the acceleration, here is positive and V will be negative. So you will see the particle move downward, that is accelerating flow. And in another way, if U is decreasing in x direction, like decelerating flow, and then here negative, minus negative equal to positive, and you will see the particles moved upward. So the up and down velocity means accelerating and decelerating. Yang, I said, accelerating flow generates downward velocity, make flow laminar, reduce mass, momentum, and energy transfer. And if you're decelerating, that is totally another way, and you will make the turbulence. So we say laminar flow means V equal to 0. Your force is dominated, energy loss dominated by shear stress. If V is non-zero, and then in the transition, and your shear stress and pressure will jointly determine your energy loss. If your one is fully turbulence, that is driven by pressure. And then we can explain why Wollongong Beach is so smooth as a minnow, because this is shaped by downward velocity. And we also show in the downward velocity, your velocity gradient, your velocity distribution should be like this. Log law is valid only in the case V equal to 0. And for V is larger than 0, and then you should have this one. We call this one is deep phenomena, and this one is a wake law. And then this is Venturi flume or Venturi pipe. From here to here, we say is accelerating flow. We can say from here to here, the energy loss is mainly dominated by shear stress, very small. So we can say roughly the energy conservation can be used. But from here to here, this one is decelerating flow. And then here, the energy loss is very large. And then the pressure force is dominant. Same thing like this one, you can see the fog can be observed only in the downward velocity dominant flow condition. And in the house, and then fresh air, cold, and then you will have this one and warm and go up. And then you can see more particles concentrated in the bottom. And here, the distribution will be more uniform. From here to here to here will be almost the same. And this is what I want to say. I want to say thank you very much and for your attention. And then I recommend you to do the experiment for your next holiday travel. At the beginning, from your home to your destination, you can put your luggage here and you can count how much money you pay for your gas station. And when you come back, you move your luggage from here to here. You will see your payment will be reduced. Why? This is the result. Because here you have the large wake volume, and then you have the large wake volume, and then you have a large drag force, you have more energy loss, and then this will be reduced one by one. So we can say Archimedes forever and everywhere. Thank you very much, everyone.